In this lecture, we're going to cover electromechanical analogies. You've probably noticed that for the past few lectures, we are dealing with models for electrical system, mechanical systems, operational amplifiers. They all boil down to the same sort of differential equations. They're all described by the same sort of differential equation. So there must be an equivalency between a mechanical and electrical system, or the equivalent a mechanical system that is equivalent to another type of system that's governed by the exact same equations. And that's indeed the case. If you have an electrical system, we can convert that electrical system into a mechanical system and make them and look at the equations that will be governed by the exact same type of differential equation. So that's the focus here, is to find these analogies between mechanical and electrical systems and convert one system into another, and see how different components in a mechanical or in an electrical system will perform pretty much the same functions. Let's think about a resistor, for example. What is the function of a resistor in an electrical circuit? It's mostly there to dissipate energy in the form of heat. And so does a damper in a mechanical system. So theoretically, they should be governed by the exact same sort of equation. We can store energy in a mechanical system in the form of kinetic energy. We can also store energy in a electrical system in the form of electrical or magnetic energy. So the inductor or capacitor could be the analogous of a mass in a mechanical system, electrical system. So that's the objective today, is to understand this analogy between electrical and mechanical systems, convert one system into another, and see what functions each element in the system fulfills. Let's just start with an electrical system here. We studied this one before. We derived the equation for it. This becomes a second order differential equation. And if you now look at the response of the charge as a function of the input voltage, these are the results here for a step and an impulse response. So for a step response, we turn the system on, a charge is developed and then settles at a given point. And for an impulse, we briefly turn on and off the voltage input. So charge is established and then dies off to zero. We can also look at the current, which is simply the derivative of the charge. We can now calculate the impulse and the step response by just taking the derivative of what you see here. And that's the result. If you look at the current, we see that even when the voltage is a step input, the final current is zero because the capacitor there becomes an open circuit. Same goes for the impulse, except that the impulse is now starting at the initial current and then decaying to zero, which if you compare these two signals here, you see that the current is simply the derivative of the charge. These graphs here are the derivative of the other graphs. Now let's look at a mechanical system. Let's take this simple mechanical system here, which is simply a mass spring damper system, and find the equations for it. We can find the equations and we can calculate the step and the impulse response and then see what happens. Not surprisingly, we'll see exactly the same behavior because this is also a second order differential equation. Now, when you talk about a step input for the force, we are applying a force and holding that force constant. So eventually this mass reaches equilibrium. And when it reaches equilibrium, the final position is not zero, it's F over K. F, the force divided by the stiffness of the spring. So the spring holds that against the force. So we're stretching the spring, and when the force in the spring is equivalent to the force we apply, the system reaches equilibrium. That's what you see in this step. The impulse response, it would be equivalent equivalent to slapping this mass, creating a lot of energy and just letting us oscillate back and forth until it settles at a given position. So you can see here the same behavior as the charge in the electrical system. Let's go back to the charge, same graphs, same behavior for the inputs, step and impulse. And here is the equivalent in the mechanical system, same sort of behavior. Now let's move on to this. Let's take the same system, and now let's look at the speed as the output, which is the derivative of position. Same system, same inputs, different output. What do we see? Well, the speed in a steady state, the speed when everything settles, goes to zero. So we are applying a force with a step, stretching the spring, eventually that stops, And if that stops, then the speed is 0, is what we see here. Same goes for the impulse response. If you slap the mass, we create a spike in the speed and then oscillates back and forth before it settles at a given point. So we see a very similar behavior to the current observed in the electrical system. So charge and current are here. If you take the derivative of the charge as the current, if you look at the equivalent in the mechanical system, that is the displacement. When you take the derivative of the displacement, we get the speed, which now turns out to be the same as the current in here. So from this analogy, we can say that we can try to see what are the equivalent elements in the electrical and the mechanical system. So here we have the equations for both of them. Equation 1 is the mass spring and damper system, sum of forces equals to ma, and that is expressed as a function of the displacement. So second derivative of displacement plus b times the speed plus kx. And if you look at the electrical system, let's do the same analysis now as a function of the charge. And we end up with a second order differential equation that follows pretty much the same structure. So from the analysis we did before, we could see that the charge and the position are equivalent. They show the same result. And their derivative, therefore, will also show the same result, which means that current and speed are the same. So if charge and displacement are the same, their derivatives are the same, which means that from charge we go to current, and from position we go to speed. So current equals to speed. And here are the two equations we got to model this system. We already saw that their results are exactly the same, but they are representing here different things. One is representing the charge, one is representing the speed. So what can we see from this analogy? Well, we can now try to combine these two equations and see what functions these elements in the mechanical and electrical circuit do, and how in which ones are equivalent. So if the mass, so we can see, let's start with this equation here. We see that in this equation, the last term there that it doesn't take a derivative is x and q. So the position and charge. Position equals to charge. If you take their derivative, then you're going to have speed equals to current. Derivative of charge is the current, and this is precisely what we see here in the second element. dx dt equals dq dt, which is speed and current. And then the last one is the equivalent of acceleration, but for us that has little interest. Now, what else can we observe from this? Well, we can see, for example, this is the most obvious one, that you have two elements multiplying the current and multiplying the speed, and that's the coefficient of viscous friction in the mechanical system, and that's the resistance and in the electrical system. So what are these elements doing? Well, they dissipate energy at a rate that depends on the speed or the current. So they fulfill the exact same function in the electrical and mechanical system. They are equivalent. They dissipate energy. What else can we see from this? Well, we can see that M and L appear in the same position in the equations here. So what are they doing? They store energy. M is the mass. It's storing energy in the form of kinetic energy, whereas L is the inductance, and that stores energy in the electrical system in the form of magnetic energy. Right, so they also have the same function. So they are the analogies of one another in different scenarios. The last element here is the spring coefficient, okay, the stiffness of the spring, and the capacitance, 1/c. So they are also fulfilling here the same job. What are they doing? Well, the stiffness is a measure of how compliant the system is to the establishment of a position. Depending on how K is, it takes more or less energy to move the system. And so is 1/c. Depending on how strong C is, it is more or less easy to let a charge establish in the electrical circuit. Right? So they are equivalent. In this case, K would be the equivalent of 1/C. And they are a measure of how compliant either system is to the development of a charge or a position in the case of the mechanical system. Right? So from these equations and from the observations we made later, we can now take an electrical system and through this analogy, convert that into a mechanical system, and both will be governed by the exact same type of differential equation, with, of course, the only difference here is what they represent. Finally, we can look at the other side of the equation here, and you have F and V. So F and V, force and voltage. Now, does that make sense? Are they analogous? And what do they do in these two systems? Well, force is what makes the system move, is what we input to the system to make a charge, to create a charge in the system. And so is V in the electrical system. So is F in the mechanical system. We apply a force to induce a displacement of voltage, induces a current or a charge, whereas a force induces a position or displacement. Right? So they are also the equivalent here. So with this in mind, we can create what we call the direct analogy to convert now a mechanical into a electrical system. And here is the summary of what we discussed. The mechanical system, in the mechanical system, the velocity or the speed is now analogous to the current. So position is analogous to charge. Force is analogous to voltage. Those are the inputs to the system. Damping, resistance. Mass is inductance. Compliance is the capacitance. Compliance 1/K. Right? So these are doing exactly the same job. Again, inductance stores energy in the form of electrical field. So does the mass, but in the form of a kinetic energy. Resistance and dampers dissipate energy. Capacitor and the stiffness of the spring now is a measure of how compliant the system is. All right, so our entire analogy here is based on this assumption. The kinetic energy in the mass is analogous to magnetic field energy in the inductor, and everything else is derived based on that assumption. Now, how do we convert one equation into another, or one system into another? And here is the key. The equations of the mechanical system will be compared with the mesh equations of the electrical circuit. And here is the key to solve this problem. This means that if we have a system with 4 loops, we'll have 4 degrees of freedoms in the mechanical system. If you have an electrical circuit with 4 voltage loops, each loop is associated to a degree of freedom in the mechanical system. So the system will have 4 independent positions. If the electrical system has 4 independent loops, 4 independent positions in the mechanical system, and so on. All right. Well, that is the key to solve that. We'll do some exercises later, and you'll see how that works. Any questions so far? It's very abstract at this point, but we'll get to a more concrete example later. Any questions at home? Oh. Well, we could take our analysis to a different domain too, and let's look at a hydraulic system, for example. Instead, in the hydraulic system, the pressure in the system would be the equivalent to the electric potential, the equivalent to what is inducing a behavior in the system. Now we apply a pressure instead of applying a voltage to create a flow rate. The flow rate, which is the equivalent to the current in the electrical circuit, is what is flowing in the circuit. All right. If we now take the pressure difference between 2 points, well, that's the electrical potential difference between 2 points, which is the voltage. All right. So the pressure difference between 2 points is the voltage that creates a flow in the circuit, and that's the equivalent of the current. If you integrate the current, which is the flow rate, what do we have? We have the quantity of fluid in the system. I've integrated current, we get charge. So the charge is the equivalent of the quantity of fluid present in the system. Let's take a look here. For example, if we have a pressure in one side here and a pressure on the other side, the pressure difference is the voltage that we would apply, equivalent to a voltage that would be applied to an equivalent electrical circuit. And you see a hydraulic resistance here because the pipe is changing, and that creates a resistance, and that is equivalent to the resistance in the electrical circuit as well. The electrical circuit resists current, whereas the hydraulic resistance will resist flow, current equivalent to flow. What else? What other type of analogy could we do? Well, we can look at the capacitance. What would be the capacitance analogous in a hydraulic circuit? Well, the capacitance is there sometimes to store energy. So what can you store energy here? Some sort of tank that stores water in the form of a potential energy. We are storing some energy that can be delivered to the system later. And a tank such as this one, for example, with two flows, one coming in, one going out, the difference there, the integral of that difference is the quantity of fluid at a time, and how much is stored now is how much energy we are storing in the system, which could be equivalent to the fluid, to the capacitance in an electrical circuit. What is the equivalent of an inductor here? What would be the equivalent of an inductor in a hydraulic system? We got the fluid tank, we got the resistance, we got the pressure, we have the current, have pretty much all the elements, but what would be the equivalent of an inductor? There would be the fluid flow inertia. And that makes sense, doesn't it? Because that's what an inductor does in a electrical circuit. It tries to maintain the current the same. It has its own electrical magnetic field energy, and so long as the current is flowing at a constant rate, it is happy, it doesn't do anything. But if the current starts to change, it will discharge that energy to keep the current going at the same rate. All right, so it's the same as an inertia. The fluid inertia exists, and the idea of the inertia is to continue to flow at the same rate, the same speed. All right, so the inductor would be the equivalent of the fluid inertia. So now let's look here at this simple equivalent circuit. We have a pump. The pump creates a fluid flow that goes through a pipe. Pipe has a resistance. The fluid goes to a tank and then back to the pump. And you can find the equivalent electrical circuit by representing the pump as whatever creates a current in the electrical circuit. That's the voltage. The resistance is the resistance in the electrical circuit, and the storage of fluid there is simply the capacitor storing energy. If you want to add the fluid flow resistance, then you could just add an inductor. The fluid flow inertia, we can simply add an inductor to the electrical circuit. Right. Now, if you derive the equations for these two systems, they will be governed by precisely the same sort of differential equation. Right. And which makes the analysis interesting. If you don't want to deal with a hydraulic system, deal with the equivalent electrical system. If you don't want to deal with the electrical system, go to a mechanical system. It will represent the same thing. You can deal with the equations there instead, right? Depending on whatever you're more comfortable with. Are there any questions? No? Okay, so let's continue. Now let's take a look at a different type of analogy, because the first analogy we made, we were saying force is equivalent to voltage, But that was kind of arbitrary. We could have chosen a different way to do that. And here is the indirect analogy that it will give us similar results. Now let's look at this mass spring damper system. That's the equation for it. And now let's look at this system, this electrical circuit, and derive the equations for that. So this one is easier to find in nodal equations and do the sum of all currents equal to the current through each of these elements. Let's call the voltage here V. And the voltage V is the same across all three elements. We know that the current I of t equals to I1 plus I2 plus I3. What is the current I1 as a function of V? We know that a V equals to 1 over C integral of I dt. So I is C times dV dt. That's current I1. What is the current through the resistor? What is the current through the resistor? Anybody? Is the voltage across the resistor V over R. And what is the current through the inductor? The voltage in the inductor is L di dt. So the current through it is 1 over L integral of V dt. Now let's look at what we created here. That's a different equation. And in this equation, things look slightly different because now our analogy is assuming that F is equivalent to the current. But what else are we saying here? We're saying that the mass is equivalent to a capacitance. And that makes sense because the mass still stores energy in the form of kinetic energy. The capacitance now stores energy in the form of an electrical field rather than a magnetic field. So that's the difference compared to the other one. The base of our formulation here, or the basic assumption, is mass is equivalent to energy stored in the form of electrical energy. And then everything else is derived as a consequence of that assumption. We're also saying that B is equivalent to 1 over R. And K is equivalent to 1 over L. Well, we could kind of see that because K is in the spring could store energy in the form of potential energy as well. And that is associated with the energy stored in inductor as 1 over L. But what else are we saying here? We're saying that the integral of V equals to X. Integral of V equals to X. We say that the derivative of X equals to V. And you say that the second derivative of X is equal to dV. So what is the analogy here? Well, the analogy is simply that a voltage is equal to speed. Voltage is equal to speed, right? Or integral of derivative. You can see from here the derivative of X equals to V. The derivative of X is the speed, and that is indeed the speed. Now, if you integrate both sides, integrate both the speed and the voltage, then we go to position and the integral of voltage. Right. So the underlying assumption that we made here is that a kinetic energy is now equivalent to electrical energy in the capacitor. Everything else is derived as a consequence of that. And the main other thing to take from this analysis is that now a force is equivalent to current and voltage would be equivalent to speed. So let me summarize this second assumption in this we call indirect analogy. So here we have the equivalent of, this is 1 over R, by the way, in this second analogy. Now, capacitor is equivalent to mass, both store energy. The resistance and the damper are there to dissipate energy, same as before, but now we see the 1/R showing. And inductance and the stiffness constant are the inductance and the spring are equivalent. They are here to store energy, one in the form of potential energy and the other one in the form of a magnetic energy. Right? And the underlying assumption is kinetic energy is analogous to the electrical field energy in the capacitor. Now, another change of this, another variation compared to what we did before, is that the equation of the mechanical system are compared with the nodal equations of the electrical system. You remember the first one, the way we derived it, we had a loop equation. And we went with the direct analogy to find the equivalent mechanical system. Now, in this particular case, it is easier to do the nodal equations to find the equations of the system, and then find the equivalent mechanical system using the indirect analogy. So you have these two options. Which one should I use is up to you. But ones will give easier results than the other. For example, in the indirect analogy, if you have to do a nodal equation to find the equivalent to find the equations of the electrical system, then go with that. If it is easier to do loop equations, then go with the direct analogy to model the electrical circuit and then find the equivalent mechanical system. They are very similar in terms of applicability, but the main difference, other than just these analogies being different, is that one is more applicable to loop equations, the other one is easier to use with nodal equations. So these are the two simple analogies for today's lecture. Now we're going to do some exercises, but before we go there, are there any questions about this? Any of these analogies? I know there's a lot of information in a very short amount of time. Any questions at home? You can type it if you don't want to speak. No? Okay, so hopefully an example will make things easier for us. Now let's do this example here. Let's try to do 3 examples if we have time. So here we have these electrical circuits, and the objective is to find its equivalent mechanical model using the indirect analogy. Indirect analogy will now require us to use the nodal equations instead of loop equations. So I'm telling you, I want the indirect analogy that immediately says we should use the nodal equations, and that, in fact, that's a lot easier in this case than it would be to do loop equations because of the current source there. So here is the procedure: label all nodal voltages and write their equations. Rewrite the equations using the analogs, the analog mechanical systems and mechanical components, and then draw the equivalent system that corresponds to the equation. So let's do that. So to start, the question again specifies that we want to use the indirect analogy, which makes more sense for this circuit because we can use the nodal equations instead of the loop equations. So the first thing is to identify the nodes and write the equations for them. Which nodes are we going to define here? Now let's start by assuming that here we have a ground that I should have written there, I forgot. That's the ground, that's 0 volts. And let's define the nodal voltages. Which nodal voltages do we need here? How many? How many nodal voltages are required to completely characterize this circuit? Oh, in each point where the voltage is different in the circuit. So that is 3. Right, 1 here. Let's call this V1. Let's call this one V2. Let's call that V3. And elsewhere is 0. So with these 3 points, we are able to fully characterize the system. Right? The last one is 0. Now let's write the nodal equations for each of these 3 nodes, starting with node 1. For node 1, we want the sum of all currents going in and out to be the same. That means the sum of currents at that point is 0. So what is the current going in? Well, that's the current from the power source, or the current source. Let's call this current I. And what is going out is the current going to the resistor. So the system must balance. And we can say that the current going in equals to the current going out, which is the voltage difference across the resistor divided by the resistance. V1 minus V2, because in this particular case, V1 is greater than V2. So they have a positive number. All right, so I equals to V1 minus V2 over R. Very good. So that's for node 1. Now let's do node 2. Again, sum of all currents in node 2 are 0. So you have current going in from the resistor, and you have a current going out towards the inductor. So they must be the same, because that's single. That's all what is at that node. So the current from the resistor, we know what that is. We just wrote it is V1 minus V2 over R. And this must be equal to the voltage across the inductor. The current across the inductor, which is, what is the voltage, the current across the inductor there? Anybody? 1 over L, integral of the voltage difference across the inductor, which is V2 minus V3 dt. It's the voltage difference across the inductor. V3 is only that point. We want to see the integrate the voltage difference, the net voltage across the inductor. And now we can go on to node number 3 and do the same. Sum of all currents equals to 0. Now we have here a current going in the node from the inductor, and you have 2 currents coming out. One is through the top resistor, and one is from the capacitor. So the current going in, we know what it is. It's 1 over L integral of V2 minus V3. And this is going to be equal to all the sum of all currents going out. Oops. And what is the current going out? Is the current through the resistor plus the current through the capacitor. So what is that through the resistor? Is simply V3 minus 0 divided by R. Why 0? Because this is the ground here. So it's V3 over R plus the current through the capacitor, which is C dV3 dt. They're all equivalent. Okay. So we got 3 equations. We had 3 different voltages using the nodal equation. This means that in our equivalent mechanical system, we shall see 3 different points where the position can change independently. 3 different degrees of freedom in the system. Right? Any questions here? Are we good with this model? Right. So here I have the model again. Sorry, this is not equal to 0 here. There's a typo. That's not equal to 0. There's also a typo there. The equations we just established, and now we can rewrite them using the electromechanical analogy, using the indirect analogy. So if you go back to our table of indirect analogy, what do we see? Mass is equivalent to capacitance. Stiffness is 1 over L. B is 1 over R. Speed is voltage. And force is current. Let's go to equation 1. Equation 1 is I equals to V1 minus V2 over R. So all this current, this power from this current is dissipated in the resistor. What is the equivalent in the mechanical system? I is F, V is the volt, is the speed. This V was a poor choice, should have called it E to avoid confusion. So now this is the speed. And the 1 over R becomes simply B. I'm just replacing everything with their analogies. And look at what we created here. What does this equation represent? The force developed in a damper. Is the force developed in a damper. So all the energy from the force is being dissipated in the damper. In the mechanical electrical system, all the energy from the current dissipates in the resistor in the form of mechanical, in form of heat. And here is the same, but now we've just created the equation for damper. Any questions before we move on? All good? Are you sure? Okay. Now let's do the second equation. Well, the first part of the equation is V1 minus V2 over R. So voltage becomes speed, and R becomes 1 over R becomes B. And this is equal to, tell me what that is. 1 over L is K. 1 over L is K. 1 over L is K right there. And then you have integral of voltage. What is the integral of voltage in the mechanical system? If voltage is the speed, what is the integral of voltage? If voltage is the speed, integral of voltage is position. Very good. The integral of voltage is position. And this makes perfect sense because you see we did need a position there to make sense of this equation, because you can only create a force by multiplying the stiffness by a position. All right? So if V is voltage, let's put it this voltage. If voltage is the speed, if you take the integral of voltage, that's position. Integral of voltage is position. Okay, so that's equation number 2. So what do we see here? Let's analyze this equation. And what is this equation telling us in an equivalent mechanical system? We are looking at a damper on one side and the spring on the other side. They are connected to the same point, and they are developing the same force at that point. That's what the equation is telling us, right? The resistor and inductor are sharing the same current, but here the damper and the spring are sharing the same force, and indeed force and current are equivalent. You see what we did there? We took the current balance, converted that into a force balance. The first equality on the top there, it says current going in the node equals current coming out of the node. We converted that into force, which means that in the mechanical system node, force from one side and the other side is the same, which is obvious. And force from one side and the other side of that node is the same. And on one side we have a damper, the other side we have a stiff spring. Let's go on. Equation 3. So 1 over L V2 minus V3, we just calculated that. That is K x2 minus x3. And then we have V, which is voltage that turns into speed. It's unfortunate that I chose the wrong terminology here, because now there's a confusion between V on both sides. But 1 over R is B. So what do we created here? Another damper plus C, which is the mass times the derivative of the voltage. What is the derivative of voltage in the mechanical system? What is the derivative of voltage in the mechanical system? Acceleration. Very good. Acceleration. Right? Voltage corresponds to speed. Derivative of voltage, therefore, is the acceleration. And that makes perfect sense because you have a mass and you can only convert that into force by multiplying that by the acceleration. Now let's see what we created in this equation here. We created another node in the mechanical system. And in this node, there's three things happening. There is a spring on one side, there is a damper on the other side, and there is a mass attached to it. Now look at these three equations and think about how to draw them together. And you see that they share some common terms. The same way that the electrical system did, we see some common terms between these equations. And these common terms are the way they are going to be linked. Are there any questions here before we move on to the mechanical part? Are we good converting these equations to their analogous, mechanical analogous? Yeah? If you have questions, ask questions. There are no stupid questions. There's a lot of information in this lecture. So, no? Everybody's good? Anybody at home? All right. So here we have the equations we just derived. This is another typo here. This is not equal to 0. I changed this last night and it was too late. These are the equations we just calculated. Now I just changed one little thing here. I took that of V3B, and I moved that to the right side of the equation, the left side of the equation, just to leave the mass times its acceleration alone on the other side. Forget about these indices here, B1, B1, and B2. They don't need to be there because we didn't specify R's that as being different, right? But if they were different, or we could call actually this R1 and R2, and then you would have the equivalent B1 and B2. But these are the three equations we found before. Now let's convert these equations now into the equivalent mechanical diagram. Let's start with the first one. What is the first one? The first one clearly is a damper. We have speed times coefficient of viscous friction that creates a force. So we have a force that is applied, or is the force developed in the damper. On one side of this, we have one speed, V1, and the other side, we have another speed, V2. Right, and that damper has a coefficient of viscous friction, B. Right, so here is the first degree of freedom of our system. That is x1, that is one displacement. And here is x2, that's another displacement. That's it. That's it for equation 1. Now let's move on to equation 2. Notice that equation 1 created this first degree of freedom V1 and V2. Now the second equation is now telling us that there is another node in the system where the force of that damper equates to the force developed by a spring. And that has got to be right there. There is a spring attached to it. On one side of the spring, we have x2. Well, that's what we just had there. The other side of the spring, we have x3. And at this particular node here, if you do a free body diagram, we go back to the equation we just found. We just started from. Right? We go back to the equation just started from. So the node in the mechanical system corresponds to this node in the electrical system where the sum of all currents is 0, Here, the sum of all forces in that node is 0 with their equivalent. Now let's move on to the next equation. Next equation is k x2 minus x3, which is precisely the force developed in the spring. To that node, we are adding the force developed by a damper. And you notice that damper is simply dependent on x3 or v3. That's B. That's this damper right there. That's the sum of all forces in that node, spring minus the damper. The damper is always going against the displacement anyways. And this is equal to mass times acceleration. I call that capital M, let me call it capital M here. Now let's look at that node again and think about this as a from a free body diagram. I could have written, or I could have put this coefficient of viscous friction B here, saying that represents friction between the mass and the surface it slides on. It's the same, right? It's the same thing. But regardless of how this is written, let's reconsider what we just made here and create a free body diagram for this particular mass. The mass would be subjected to 3 forces. There's a force coming from the spring, which is k x2 minus x3. There's friction in the mass, opposing motion. And the mass then accelerates with acceleration a3. And if you do the sum of all forces in that mass, we go back to the equation we just started from. So that represents this node. And you see that the mass now represents the capacitor. And this damper represents that resistor. Isn't this fun? You take a mechanical electrical system, we can convert it back and forth, and they are governed by exactly the same equations. If you don't want to deal with this electrical circuit, deal with the equivalent mechanical circuit. Or, how about that? We have a mechanical system to simulate, and you could simulate the behavior of that mechanical system by creating an equivalent electrical system, a physical mechanical electrical system that corresponds exactly to the behavior of the mechanical system, and then use that information, for example, in some sort of control system to control the behavior of the mechanical system. So we could, for example, experiment with the different inputs to this equivalent model, watch the outputs, then select the best combination, and then give that to the mechanical system in the form of a force. Right? Or you can do the opposite as well. Imagine that we are simulating, we are dealing with some sort of sensitive equipment, a satellite or something like that, a mechanical system, a robotic system, where we can simply experiment with the system and giving forces all the time and see what happens. But we can instead create the equivalent electrical and then study the behavior using the electrical system. And once we are satisfied, then go back to the mechanical system and use it that way. Any questions? Yeah. Yes. Yes, you could put also facing the other side. Doesn't matter. Yeah. Yeah, we could put it face the other side, or we could put it here. It's the same thing. Okay. Any questions? Any more questions? No, it's not very hard. You'll see it's always the same thing. Okay, so if there are no questions, we're going to move on to another one. Yeah? Okay, let's do this one. And this one here, it says, convert the following electrical circuit into its analogous mechanical model using the direct analogy. I like the direct analogy a lot better. To me, it makes a lot more sense than the indirect analogy. Is more tangible. But this one indeed works better with the direct analogy. So let me give you one hint. Look at capacitors in the system. If the capacitors are not grounded, don't go with the indirect analogy. If the capacitors are not grounded, go straight to the direct analogy, because it's going to be a nightmare to find the equations otherwise. So that's a good indication. If a capacitor is not grounded, direct analogy. If the capacitor is grounded, it might be easier to go with the indirect analogy. In this case here, it's easier to study the system with loop equations anyway, so it would make more sense to go with the direct analogy. So let's do that. If you're doing the direct analogy, we are now looking at the loop equation. So each loop in the system here gives us a degree of freedom in the mechanical system. So let's call this currents I1, I2, and I3. What is the equation for loop 1? Well, the input voltage is equal to R times I1 minus I2. For the second loop, we have R times I1 minus I2 plus 1 over C integral of I2 minus I3 dt plus R times I2 minus I3 equals to 0. What are we doing here again? We are doing now the sum of all voltages, and you want that to be 0. Before we did the sum of all currents. Here, the sum of all voltages, we want that to be 0. So just doing the loops like that. All right, this should be relatively straightforward at this point. Have I made any mistakes here? Yes, I have. So this should be I2 minus I1. Maybe you're now following I2, so it's I2 minus I1. And then I2 minus I3, I2 minus I3. And then the last loop there, we are now following I3. What do you have? We have the capacitor, 1 over C integral of I3 minus I2 dt, plus the resistor, I3 minus I2, and plus the inductor, L times di3 dt equals to 0. Okay, all three equations. One equation now gives, one loop gives a node in the mechanical system. Here are the equations again, just rearranged a little bit, same equations. And now let's convert these into their equivalent mechanical, but now we are using the direct analogy. So we did here sum of all voltages equals to 0, and in the mechanical system, we are going to do the sum of forces equals to 0. So we did sum of currents equal to force and force before, now it's sum of voltages and force. So in this case here, we have current is equivalent to voltage, force is equivalent to, we have force is equivalent to voltage, current is equivalent to speed, and they have mass and inductance, B and R, and K equals to 1 over C. So let's rewrite these equations, starting with equation 1. So 1 is a voltage that becomes a force. B becomes, R becomes B, and the current becomes the speed. So V1 minus V2. If you go to equation 2, current becomes speed, R becomes B, 1 over C is now K. And what is the integral of current? Well, current is speed. If current is speed, the integral of current is position. So integral of I, integral of current, position. And then plus V2 minus V3 R. Sorry, there's a mistake here. This is plus, and this is equal to 0. Right? And then finally, equation 3. Equation 3, you have 1 over C, that's K. Integral of current, if the current is the speed. So integral of current is
There.
position. Yeah.
For the second equation, shouldn't the R be a B?
Yes, should be a B. Yeah. Thank you. Yeah. So let's continue here. Minus x2 plus current is the speed. B and L is, what is L is M. And what is di3 dt? Current is speed. The derivative of current is acceleration. So M times acceleration 3. And that is 0. Good. Okay, here are the equations we just found. I rearranged them a little bit, just change the signs around to make the analysis a bit easier. And once again, let's repeat that. In the mechanical system, in the electrical system, we now did sum of voltages equals to 0. Now we are doing sum of forces equal to 0. And that is because force is equivalent to voltage. Starting with the first equation, we created a damper once again, and that damper represents the resistor there. So the force Fa is the force developed in a damper of coefficient of viscous friction B. One side we have V1, the other side we have V2. That's equation 1. That will give us a node here where V2 appears. And you see that on the left side of the equation, we have the damper. On the other side, you now have 2 elements added together, B and K. So this is likely a spring and a damper. On one side, you have V2 or X2, and the other side, you have V3 or X3. So this is K and this is B. And now that we created a third node, we can go to the last equation, and you see that on the one side of the node, we have the spring and the damper, exactly as we just modeled there. Right, that's already taken care of, and that is equal to the acceleration of the mass. So we can simply multiply this or attach the mass here, M, and this here in this point, we have A3 as well. That is the equivalent system there. Okay, and once again, now you might be confused. Why is this damper now positive? The other one was negative. Now we need to really analyze the mechanical system and figure out how we if the way we represented that is correct or not. And this one, indeed, if the force is coming from the right, the force of the damper plus the force of the spring are accelerating the mass. They're both positive. Whereas in the other case, the damper was opposing the mass and was negative. So everything was opposing the mass, the speed, and it was negative. So everything makes sense.